Okay, you guys, let's talk center of mass and calculus. So in class, we were looking at this formula that we use for a system of points. And so assuming we're going in the horizontal direction, if we want to find the center of mass, what we're doing is we're taking the mass at the first point times its position from the origin. Usually the Cartesian plane, just putting in an XY axis really helps you. It's pretty obvious where you want to put that. And then you take your second point, mass times position from the x-axis, and your third point. Oops, yeah, that's right. And so on and so on and so on. And eventually you're going to take all that and put it over the total mass. And that is great for a system of points. This was our simplified version where we're taking this constant value of 1 over the total mass times the sum. Remember, that means sum of m, I, x, I. And that, of course, assumes that we've got, you know, multiple points here. So dot, dot, dot. And off we go, and we keep on going. Now, a system of points has limited use, quite frankly. So when we have extended objects, we're going to use calculus to find the center of mass. And so what I'd like to do is show you a couple of examples that we use, some standard examples, and these are ones from your textbook as well. Not that we use that for much more than a doorstop sometimes, but they are in here. So when we have extended objects, we're going to be looking to use calculus. Now this is the format that they use in the book, right? So you've got a larger mass, you've got a mass of an infinitely large number of particles, all at some distance r. Now this is the, like I said, this is the formatting they're using in your book. They're using r for a radius. The arrow just means it's a vector quantity, so not to worry. And instead of doing each of those points, because we have an infinite number of points, what they're going to do instead is take the sum, right, the integral of those little points, and we're going to slice everything up into very, very small masses and small radii and add them all up, okay? So what I'm saying here is that this is a very small mass for this object, or this element of the object, this piece of the object at position of vector r, okay? That's generally how your book likes to present it. Now, what I want to do is to show you two examples, and let me move the page. Oh, here we go. Yes, get a clean page. So our first one that I'm going to show you is if we have a uniform rod. So if you have something like even a meter stick has far too many points for us to use a system of points to find the center of mass. However, it should be half the length. My goal is that we're going to show the proof of that. That's what we want to go with here. All right, now the nice part about doing this as a recording is that if I go too fast or you miss a part, just stop, go back. Now I'm going to number all the steps here, and we're going to use some symbols we haven't seen before. All right, so let's start with a Cartesian plane. There we go, and I'm going to put in a bar. And remember, we're going to slice this bar up into teeny tiny pieces, right? We're going to change the mass along those. And of course, this is my y and this is my x. And from here to here, we're talking about length L. So, you know, these are really equivalent. And that's going to become important for us a little bit later on. Okay, so we're going to take this bar and we're going to slice it up into teeny tiny pieces, and then we're going to add all those teeny tiny pieces together. So instead of this, which is the way I would normally look at it if I were dealing with a system of, or a collection of points, This is the way your book likes to present it, right? We just sort of did it backwards, right? Instead, what we're going to look at is still going to multiply by 1 over the total mass, but we're going to add up this little collection of small masses and the radii away from, you know, their space away from the origin. Okay, so since we're dealing with this object here that is extended, here's the first thing we're going to do. The first relationship we're going to look at is what we're going to call the linear mass density. Now density, I know you know what that is. That would be mass over, whoops, I can't spell. Oh wait, I have an eraser, I forgot. There we go. Let's try that again. There we go. All right, so linear mass density. I know you know what density is. It's mass over volume, but we're not going to deal with volume here. So we're going to look at mass over length. All right, because let's face it, as we change the length, we're changing the amount of mass that we're working with. Now your book uses this symbol lambda. Now for me, that's the symbol for wavelength, but it's okay. All right, at least we're not going to confuse it with something else. So mass per unit length is what we're going to consider the linear mass density. You know how much I love fractions, so let's change things so that it is in a line. And again, we are going to take little pieces of both of these, right? So lambda change in L equals the change in mass. And let's face it, we know from over here that X and L are equivalent. So I'm just going to change the formatting that I'm using right there. Okay, so now that we have this relationship, let's move into part number 2. I'll change colors for that. Let's go to green. That sounds kind of fun, right? So number 2. All right, there we go. Number 2. All right, let's start with our calculus expression. If we're going to find the center of mass, we're going to take 1 over the total mass times integral of x dm. All right, now if you take a look at, oh, whoops, I just saw something I wrote wrong. Let's change that a little bit. I put some, oh, no, I got this one too. Isn't that always the way? All right, let's try that again. Let me grab my black pen. All right, I just want to rewrite this so it makes sense. Right, and we said that X and L are equivalent. So I put too many equal signs in there before. I'm sure somebody was yelling across the way. But there we go. That should be fixed now. All right, let's go back to where we were. All right, so as you can see, I want to take this and change it right there. And I want all of my variables to be the same, which is why the X becomes so important versus having it in terms of L. But luckily, they are exactly the same thing. So I'm doing 1 over m, and I'm going to put in x lambda dx. Now, lambda is a constant, so we're going to move the constant out over here. Like, we're not going to take the integral of a constant value. So lambda over m integral x dx. Now you are ready to actually take the integral, and then we will multiply through the constant that we had from before. This one is actually not too tough to do, right? So remember, we're going to add 1 to the exponent. It was 1, now it's 2. We're going to take that new exponent and we're going to put it under the coefficient that I had to start with. Okay, so 1/2 x squared. That's going to be what my integral of x dx is. Now, what I need to do is get a new page because I am totally out of room here. So let me step back so my shadow doesn't hurt me here. And let's start again. I'm just going to rewrite so I know exactly where I was. So I had this before, and then I took the integral of that, and I ended up with squared 1/2. Right, now I'm going to multiply that by my constant that I had before. Right, so I'm going to get lambda on 2m x squared, which looks like gobbledygook, right? But remember, we have a value for lambda from before. Lambda is m over L. We know that L is x. Well, actually, never mind that part. We'll just keep it in terms of L. We're going to go back to L because we want to evaluate it. I'll get the hang of this eraser eventually. There we go. All right, so if I substitute it in over here, we can get m on L on 2m x squared, right? My L's are certainly going to head on out here, so what this is going to change to, of course, this is going to cancel. We're going to get 1 over 2L times x squared. All right, now let's evaluate. I'm going to take this and I'm going to come down here and I'll just evaluate it. I want to evaluate it from 0 to L. Now if I go to do that, I'm going to start with my L. I'm going to plug it in for x because that's where that's going to go. So I'm going to get L squared over 2L. That's my first quantity. And I'm going to subtract the quantity I get when I put in 0 for x. And it's fairly obvious that that's going to go away. And one of these is going to cancel out over here. And I'm going to be left with ln2. So it's exactly what we thought it was going to be. And you think, gosh, that was a lot of work just to figure out something that I think I already knew. But it gives you an idea of what we're doing here when it comes to center of mass in calculus. Every once in a while, you're going to end up with these extended objects that are just a little bit crazy. So we have to have a way to evaluate them. And I want you to at least be exposed to how that is done. All right, I'm going to pause for a minute and we'll be right back with the next example. Okay, here's our second calculus example. This is going to be for a triangle. And this one's a little bit crazy. All right, in your textbook, in case you want to check out where it is, it's on page 249. So again, I'm going to draw a Cartesian plane. We're going to put in a triangle. Well, not so straight, but you get the idea. All right, we're going to label the sides. And again, remember, what we're looking to do is to slice this up into teeny tiny pieces and add them all together. Okay, so as we go about this, we are changing from here to here. We are taking, obviously we're taking a little bit of a distance, right? We want to take little slices of distance. At the same time, we are also taking little slices of mass. Okay, this is actually at, y above the x-axis, right? It's at a position of y. And we are going to use density again. Now for this one, what we're going to take a look at, we're going to actually give it a different variable. It's not going to be lambda anymore. We're not going to look at a linear density. All right, so usually what we say is that density equals mass over volume. Okay, so volume times density, again, let's get out of the fractions, equals mass. Now, the volume of this triangle is going to be, let's substitute for that. It's going to be the change in x times y, how high up it goes, right? Because, length times width. And then we've got the thickness of it as well. T for thickness. That's what I'm going to remember that one. All right, so there's my volume. Now, in your textbook, they use a different letter here for density. It's called rho. To me, it looks like a P with a giant fat tail. What can I tell you, right? And again, because this is the first expression in parentheses for our volume. This is still for our density, and our mass, we're slicing it up into teeny tiny bits. Remember? Okay, so we're going to work with this expression, and we're also going to work with, let's see if I can squeeze it over here. We're also going to work with the Well, let's put a big fat tail on there. There's rho. Mass over volume. We need to get rid of some of these variables. We have way too many of them. I'm not even close to being able to do calculus yet because there's like 100 different terms we're using here. We need to simplify. So here's what we're going to do with that. All right, so P equals, if we're going to do, again, the volume of that triangle, it is a triangle here. All right, we're going to look at 1/2 the base of my triangle, which is A. Right? B is the width of my triangle, and then again, thickness of my triangle. So that's going to be another expression for the volume. Now that doesn't seem very helpful, but just bear with me. It's gonna make a little more sense in just a moment. Okay? Okay, we're good. Now, what I want to do next is I'm going to take this and get rid of it. Okay, so I'm going to put this expression right there. That is my third piece. So let's see, we got 1, we got 2. I guess I can go over here. Number 3, we're going to start changing things about. All right, so we're dealing with this expression, the dm expression from number 1. And I'm going to put in dx times y times the thickness. Then I'm going to substitute for rho. I'm going to get rid of that density one, and I'm going to at least try to start simplifying some of these. Okay, what that does is it also gets rid of the thickness. So if you're thinking, okay, this doesn't seem to be too much better quite yet, just again, bear with. All right, let's rewrite it. We're going to have, we'll get that 1/2 out of the bottom, so 2 my over AB dx. That's going to simplify out because I'm going to take, yeah, let's do that. We got that. The 2 has to come out of the bottom, da, 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 equals d and times dx. I'm going to keep the dx over here. It's starting to look a little more like calculus. In fact, so much so, maybe I ought to put that calculus expression in there, huh? Okay, so let's go to our calculus expression that we're supposed to have. And if we want to find the center of mass, what we're trying to do is take the sum, 1 over the sum of the particles, times the integral x, and we're looking for the change in x with respect to mass. Okay, now if we take a look at what we've got here, I have an expression for dm, and if I put it in there, if I get rid of this by substituting this one, then I'm going to have it as x dx, which is where I want to go. So let's rewrite 1 on m integral, right, x, and times 2my over ab dx. I'm getting closer. I'm getting closer. Okay, so my next thing I'm going to do is I'm going to pull out my constants. This is one of my tricks here. You don't integrate constants, so we'll pull out the constants. What are my constants? My constants are, obviously it's 2, right? The mass, the m is constant, right? My y is constant, or I'm sorry, a is constant, no y. And then b, right? 2ma and b. Okay, so we pull all of those out, and what am I going to be left with? Oh, I'm going to need a new page. All right, move out of the shadows. Let's move on to a new page. Okay, so we're going to pull out those constants, and what I'm going to end up with here, call this one number 5. All right, so I'm pulling everything out from what I had before. I still have my 1 over m, that was from before, times, now what was over there? The 2 and the m were on the top of the fraction, right? And on the bottom, we had a and b. So we had those. We'll leave this here, x, y, dx. We're starting to clean things up just a little bit. Okay, that'll go away. So we've got 2 on AB. We're so close. That y is just causing some problems here. all right, because we can't do the integral with you know, a y stuck in there. It doesn't match the other ones, right? So this is where your brain might pop just a little bit if we're not careful. Again, doing this completely on your own, that's not what I expect you to be able to do, but I do want you to recognize how we're going about and some of the techniques that we use when we're dealing with doing these crazy looking integrals for right now. All right, so here's our trick. Here's how we're going to get rid of it. We're going to use the slope of the line. Remember from our previous page, we had that lovely graph with the triangle on it. All right, so to express y in terms of x. Okay, so based on what I had before, right? Y equals mx plus b, right? My slope was 0, right? And what is, or I'm sorry, my y-intercept was 0. I said that wrong. And what is my slope? Well, the slope is the rise over the run, right? Correct? So b over a times x. Well, those were constants that I had from before, so this shouldn't be too tough, right? So I'm going to take this and I'm going to put it there, and I'm going to end up with something I can work with. All right, so that's my next step here. That is my next step. I'm going to say 2 on a b integral, and we're going to say x times b over a x dx. Now I know that b and a, let's get that, so it looks like a b. These are constants, so again, I'm going to pull them out. 2 on ab times b on a. And I'm going to be left with x squared dx here. All right, so now this part is looking pretty good. I'm going to be able to do something with that. These constants, let's see, my b is going to go away. I'm going to get 2 on a squared integral x squared dx. Lord have mercy, we're finally ready to take the dang integral. Hallelujah, right? So we're going to add 1 to the exponent. We're going to take the new exponent, we're going to put it under the coefficient. Whew. And then we're going to multiply it by our constants. Okay, so what I'm going to end up with here, we're going to finally finish this bad boy up. We got 2x to the third over 3a squared. And we need to evaluate that from 0 to a, which is the, well, it's like the L from the last problem. It's the length of our triangle. Okay, so again, we're going to put in a where x is. So, and we're going to start with our bigger one, where we have it as a. So 2a cubed over 3a squared minus 2 times 0 cubed over 3a squared. All right, so that one goes away. That makes life a little bit easier. And so what we end up with is 2/3 a, because that cancels and we're left with one of these. Ta-da! Holy Moses. All right, so in the x direction, my center of mass would be right here. Okay, please don't go and memorize all of these. All right, but get an idea of what we're doing here. As you become more fluent in integrals and calculus, if you look back on this a little bit later, you'll go, oh yeah, okay. I mean, the whole linear density piece is wonky. And if you didn't know to do that, I don't know that you could simplify the expression enough that you could actually take the integral of it. So it's helpful to have that. But otherwise, every once in a while, you are asked to come up with a relationship and an expression to show what your center of mass, or in the case sometimes when we are in rotation, like what is the rotational inertia of something. Again, a term you're not really aware of yet, but we do take some of these these extended bodies, and we do some of this crazy calculus stuff with it. So I wanted you to see it, but I didn't want to just make everybody weep in the middle of class. All right, so make sure you have it and that you have a pretty decent idea of what I did here. All right, but again, I'm not going to ask you to recreate this, so please don't waste a couple of hours trying to memorize this dopey thing. All right, just kind of get a feel for how it's working and what we're doing. And that way, when we get to rotational inertia, you're going to be able to use that. Most of the time, if you have to find center of mass, you're going to be just using the original expression we use for a system of points. So no worries there. But now you've got a little bit of background on some of the calculus we can use for our extended bodies. All right, good enough. Have a good night.